talk just for a little bit about the properties of alcohols. We said earlier that they're a lot like water, and that's true. And there are certain characteristics of alcohols that are shared with water that make them very important as solvents or in reactivity in organic reactions. And the first thing is hydrogen bonding. We know water can hydrogen bond, and alcohols can hydrogen bond too. So let's remind ourselves what hydrogen bonding is. Here's a video of water molecules interacting. And as you can see in this video, we have polar water, right, with a dipole moment, partial negative charge on the oxygen, partial positive charge on the hydrogen. And the lone pairs on the oxygen can nestle up close enough to the hydrogen, because the hydrogen is so small, to share those electrons with the hydrogen. It's almost an ionic-like bond. It's a weak sharing of electrons, but it's a bond. And when you have a lot of water molecules together, they're able to arrange themselves in a nice array where these hydrogen bonds are maximized. This is why water is denser than ice, because the freedom of the liquid state allows optimization of this close hydrogen bonding to occur. And with alcohols, we get this occurring too, right? We have that OH bond and alcohols, and oxygen is small enough to get close enough to the hydrogen and to share those electrons with the hydrogen, causing a nice hydrogen bond. Now, here's a video I found which is hilarious that talks about the importance of hydrogen bonding.
The wondering marvel of hydrogen bonding. Hydrogen bonds, bucking a pond, walking across, some looking lost. Why don't they fall in? Surface tension. Hydrogen bonds, hydrogen bonds, hydrogen bonds, hydrogen bonds. Small molecules, they aren't fools. They can attract, they won't attack. H positive, O negative. Opposite ends, they become friends. Hydrogen bonds, hydrogen bonds. H2O small, watch it liquid at all. CO2 gas, it's got more mass. H2O's got hydrogen bonds. Buzzing and cross, walking the pond. Capillary action you see, cause it must be a high D electronegativity difference. Got polar ends, the molecule bends, the O at the joint, high boiling point. It's not volatile, just not in style. Hydrogen bonds, hydrogen bonds, hydrogen bonds, hydrogen bonds. H on one side, and ORF on the other. It's really polar, and attracts like a mother. Dipole attraction from hell. I love hydrogen bonds so well.
Okay, I like that video, but it points out some important things about hydrogen bonding, whether it's water or in alcohols. Alcohol will have a much higher melting boiling point than the corresponding alkane or alkyl halide, and the reason is because of greater dipole interactions, because of a carbon-oxygen or oxygen-hydrogen bond. But then also true hydrogen bonds, right? You need an oxygen, nitrogen, or fluorine bound to hydrogen in order for those hydrogen bonds to occur in any significant level. And while they are not very strong bonds, a lot of them together can make a big difference and are responsible for surface tension and other things that we see in water and in alcohols. Now, the next property of alcohols we're going to talk about really quickly is their acidity and basicity. And so if we consider alcohols, again, sort of like water, they can act as weak acids or weak bases, right? Here's a reaction shown where the alcohol is shown as a weak base, right? It is abstracting a hydrogen from an acid, becoming an oxonium ion, and releasing the conjugate base for that acid. It does this very weakly. The corresponding other reaction, let me see if I can get this in place, is when we have an alcohol group, ROH, and it loses a proton acting as an acid. And this results in conjugate base, is called an alkoxide. Okay, alcohols can do both of these things weakly, and we've talked about the relative strengths of acids and how alcohols can fit in there. Now, there's one exception to alcohols in terms of their acidity, and that's with a special alcohol that we almost consider a distinct functional group, and that's phenol or phenol. You hear it said both ways. Really, when you have this alcohol group outside of a benzene ring or a phenyl ring, this is a much better acid. Much better acid than a typical alcohol. And since we've already talked about what makes things good acids or bad acids, we might be able to think a little bit about why phenol is a better acid than a typical alcohol. Really, our previous work in this said, well, if you want to know whether something's a good acid or not, look at its conjugate base and see how stable that conjugate base is. The more stable the conjugate base, the better acid it's going to be. And so this is the conjugate base for phenol. We call it phenoxide. Right? If this was a methyl group for an R, we'd call it methoxide, or ethoxide is the conjugate base, the alkoxide. Just looking at this, how do you think phenoxide is stabilized? Through inductive effects or through resonance effects? Hopefully, you look at this and you're saying, well, there's a bunch of double bonds here. I've got all these lone pairs. There might be some resonance stabilization of this phenoxide, and that is true, right? If we're to look at the possible resonance structures for phenoxide, we've got a lot of them. Here's our phenoxide over here that's lost its proton. You might think here's some electrons. Well, let me draw it here. Here's some electrons that can come in to form a double bond between the carbon and the oxygen. These electrons can come out to form a lone pair on this carbon to form this resonance structure. Those electrons could come in to form a new double bond here. Let's see if I can draw that, and I can't. These could come out to form yet another resonance structure and another resonance structure. So the reason why phenol is a much better acid than typical alcohol is because its conjugate base is very resonance stabilized. Now, it's still a weak acid, but even weak acids can be really dangerous. We had a technician when I was in graduate school who had a big jug of phenol. We use it as a solvent a lot in biochemistry. It's very good at dissolving things like proteins. And so if you want to clean up a DNA preparation, you can do an extraction with phenol and rip away a lot of the contaminating protein. This technician had a big jug of it and was sort of waltzing through the laboratory when the jug slammed into a bench and broke, and all of that went down her leg. Now, it's a weak acid, but it was enough to give her second-degree burns and permanent scarring down her legs. We'd also have to be really careful with this as a solvent because we're doing extractions, so we were trying to mix it with our DNA preparation, and oftentimes it would spray out and cause burns. A lot of time when you're doing this in a little Eppendorf little plastic tube, everything you're doing is sort of at eye level. So it's very important to have eye protection on in order to save your eyes if phenol came spraying out of a tube that wasn't closed properly.